Hi, and welcome to Demystifying Math. Today we're going to be working on improper integrals of the form x to the a. What we want to do is figure out what values of a would the integral from 1 to infinity of x to the a converge. Let's start by looking at values of a that are greater than 1. Let's suppose that a is equal to 2. That would give us the function x squared. Well, as x goes to infinity, x squared is an increasing function, so the area under the curve continues to increase. The same thing would happen if we had x to the third. It's an increasing function, and the area under the curve continues to increase as we go out to infinity. So we would say that these two integrals would diverge. Okay, so what we saw in the last slide was if it is an increasing function, the integral diverges. So we need it to be decreasing in order to converge. In addition to that, we need the limit of the function as x goes to infinity to be 0. Are both those things true if a is between 0 and 1? Let's look at some examples to find out. Suppose we let a equal 2/3. Then we would have x to the 2/3, which is an increasing function. So as we go out to infinity, the area is going to continue to increase. The same thing happens for x to the 1/4. As we go out to infinity, it is an increasing function. It's just not increasing as fast as x to the 2/3. So the area under the curve would continue to grow, and we would say that the integral is divergent. Okay, so what would happen if a equals 0? Would the integral converge? Well, if we said a equals 0, that's x to the 0. So that just gives us the function of 1. And the limit of 1 is 1. So already we know that because the limit is not going to 0, that it's going to diverge. Let's look at the graph. The area under the curve is going to continue to grow as we go out to infinity, because we're adding on more and more area as we go out. Let's see the integral and compare it. If we take the integral of 1, we'll just get x. Then we're going to plug in our endpoints of integration, and we get b minus 1. Well, as b goes to infinity, the negative 1 becomes totally insignificant, so we're just going to get infinity here. So you can see that this is a divergent integral. Okay, so what about negative values of a? What would happen? Let's let p equal negative a. Let's make it a little bit easier since a was already a negative number. That gives us x to the negative p, or 1 over x to the p. And we want to take the limit of the integral. So integrating as we normally do by adding 1 to our exponent and dividing by the exponent, then plugging in our endpoints of integration, we end up with this. So our first term involves a b, the second one does not. So this is just going to stay the same. But the first term, we need to figure out what happens here for different values of p. So taking our limit and rewriting it, we get this. So let's see what happens from here. For what values of p will the limit exist? Well, at p equals 1, it's going to be undefined. So that's not going to help us much. What about p being a negative? Well, if p is less than 1, then p minus 1 is a negative, and that limit's going to go to infinity. Let's look at an example to see why this is happening. Let's suppose that p equals negative 3. Then we would have b to the negative 3 minus 1. And in the numerator, we would have b to the 4th, flipping it over, getting a positive exponent. That's going to continue to grow. It really doesn't matter what's in the denominator here, because the numerator is going to infinity, as long as the denominator is not 0. Okay, so let's look for values of p that are greater than 1. Then p minus 1 is going to be a positive number. And the limit is going to go to 0, because we now have our b staying in the denominator, getting bigger and bigger. So 1 divided by a really large number is going to give us 0. So that means going back to this original limit that we had up here, that this first term is going to become 0. And all we're going to be left with is the second term. Since we had a double negative here, we cleared it out. So we have 1 over p minus 1. And remember at the beginning we let p equal negative a. So we replaced it with negative a here and simplified. So that means for p-values that are greater than 1, the integral is going to converge. And it's going to converge to negative 1 over a plus 1. Okay, since p is greater than 1, that means that a has to be less than negative 1. The integral converges to negative 1 over a plus 1, and for all other values of a, the integral diverges. Let's try this out. Let's let a equal negative 3. That gives us x to the negative third, negative 3, or 1 over x to the third. And that limit is going to 0. So the first part of our requirements is satisfied. The second part, we have to figure out whether it's a decreasing function or not. So let's take our first derivative to do that. So we now have negative 3 over x to the 4th. The only critical point on that function is at 0, where it's undefined. So that means we only have to test within our interval that we're concerned about and see if it's increasing or decreasing. So testing x equal 2, we get a negative. So that means that x to the negative 3 decreases from 0 to infinity, which means that our integral should be defined and should go to negative 1 over a plus 1. So let's see. Let's evaluate our integral. And we get negative 1 over 2x squared. Plugging our endpoints of integration, the negative 1 over 2b squared is going to go to 0. b's in our denominator, so it's just getting bigger and bigger in the denominator, which means the fraction is going to 0. So all we're left with is 1/2. Now remember we said this is negative 1 over a plus 1. So our a in this case was negative 3. So it works out to be 1/2. Okay, thank you so much for tuning in to Demystifying Math. Hope this helped you with some of your improper integrals. And see you next time.